Hey folks, it's T2sday. I'm going to do the same thing I did last time, which is kind of like just give a little mini talk in sort of the scientific academic head, because that's just sort of what I'm more comfortable doing, and I'm thinking being comfortable is a good thing. So I'm going to try to talk about this idea of flat reality, and I am probably going to completely muff it, but it does actually connect to T2 just in a way that's not super obvious. So, and it's probably all going to run long because that's what typically happens when I'm struggling to express something. So we'll see. I'll keep it as short as I can. So today we're going to do the background again. This is my academic talk mentality. You should always start with the beginning of the universe. Now, one of the things about this particular work and the stuff that I'm doing in general is that it comes in so many different directions. It's not like there's a single beginning of the universe. So I want to do a different one today and then talk about what I did in July and talk about the goals for August. Same as it's a T2sday update. So today I want to start with the living computation idea, and this has been, foundational to my thinking for decades now. Living systems and computational systems turn out to be the same thing. Now, a lot of what we've been talking about, like in the T2 tile project, for example, the digital replicators, the diamond replicators that people who are watching the live stream may have seen in the waiting room. Are an example of using sort of living systems principles to inform the design of computational systems. But if we're saying they're the same thing, it should go the other way as well, that we should be able to take living systems, living organisms like, say, you and me, and use computational concepts, language, all that kind of stuff to understand and describe stuff that's happening to living creatures. And that's what I want to do today. Last year, Lou Wilson, Toad Pond, and I wrote this paper, Dialogues on Natural Code, and that it was exploring that idea that we are living systems, but if living systems and computational systems end up being the same class of systems, then this language that we use, that we're always gabbling to each other all day long, hearing and speaking or not listening, whatever it happens to be, and so there's, a fundamental question about language is how does language acquire meaning? The alien comes down from space and goes gigaflocko googie, and you say, well, and I'm sorry, I don't know what that means. But if you can take the code, the gigaflocka googie, whatever it was that I just said, and put it together with an example on gigaflocka googie, then maybe it means box, or maybe it means Raspberry Pi, or maybe I have a warranty claim from the alien, or the color red, or who knows what. But at least there's an example to work with, and you can start to close in on the meaning. So that's a lot of what science is that you're developing code like laws of physics, F equals ma, or you're describing plants, a duck-billed platypus, lays eggs, but it's a mammal, or, whatever the thing is. So you have a bunch of stuff that's code, D-U-C-K, duck, and then you show an example in the real world about, here's an example of a duck, quack, and so people can learn language that way. But what if you want to talk about things that don't exist, that you can't point to an example of them? Well, so what we do is, I'm going to make a game that nobody's ever seen a game like this. It's going to be so amazing. What we have to do is we have to pick some things that do exist and say not that it is one of those things, but that it's like one of those things. And you say, well, it's kind of like this and it's kind of like that, and it's got a little bit of extra. It's like the high concept in, Hollywood. It's like Die Hard meets Sleepless in Seattle, or whatever it is. So here, we're saying, imagine the universe as a cellular automata. Now, again, there are some famous people, some rich people, who want to go way farther than that. They want to say the universe is a cellular automata. Not only that, it's a deterministic, synchronous, etc. Anyway, all these other things that strike me as, silly in the extreme. But we're not saying that. We're saying, no, we are coders. We're talking about building a framework for describing stuff. And the question is what's a good framework that allows us to do things, allows us to describe the sort of stuff that we want to describe effectively in a way that people may get, and so forth. And so we're saying, let's imagine the universe out there, whatever it is, this blooming, buzzing confusion. Let's imagine it as if, let's pretend, let's say, for purposes of modeling, for purposes of developing some code, that the universe is an actual cellular automata. And then you say, is it really? Is it binary? Yeah, whatever. No, the point is, as code developers, we have to pick language. We pick code, we pick nouns and verbs, we pick DUCK, we pick cellular automata, whatever it is. To describe things, and they're not all equally good at describing stuff. And even if they are equivalent in some sense, that doesn't necessarily mean they're as easy for people to learn or as intuitive or so on and so forth. So the idea is, if we could take some single spatially distributed model of computation, some spatially distributed, robust first programmable architecture for computation, then we could use that as a reference architecture to say, when I'm describing a machine, when I'm describing a thing, I'm describing it in terms of this particular model, that we're imagining the universe is kind of like that. Are we saying it really is that? No. Are we saying it's exactly like this? No. Are we saying that if we build a thing in this actual cellular automata, it will behave exactly the same as the universe behaves? No. But there may be useful connections anyway. Whoops. I have to stop hitting my next button before I'm ready to go next. Maybe it's a hint. So the idea is, if we could have a systematic model of computation that we could use to describe any physical thing, no exceptions, no bullshit, and if there was any question about, is this thing, this description, I'm saying, what is free will? Free will is a computation of this sort, and it has, these properties and this, and if people say, I don't get that, and say, well, we could unpack it further. We could implement a machine that does whatever it is. And my suggestion is that would be extremely powerful. I mean, almost dangerously powerful. That if there was a single uniform language that sort of truly was, in this sense, a neutral point of view, that you could describe anything. And it would be, describing it in crass physical terms, matter and energy, stuff piled up, fall down, do this, whatever, like that. It's no way meant to capture everything. But the point is, it's one systematic language that could cover everything. That is very, very powerful, I suggest. And so really, when I'm doing the mobile piece machine to build the T2 tiles and now on to the T2.5, in my mind, what I'm trying to do is actually build an example, a prototype of the spatially distributed robust first model that could be an underlying basis for saying, let us compute, for saying, well, you're saying blah, 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 I'm saying blah, blah, blah. I can explain what I mean in terms of the machine. If we take what you're doing and also put it into the same language of the machine, we can see the similarities and the differences. That's the idea. All right. So that's our background. Almost 10 minutes shot. What did I do in July? Well, I got ready for Blackhole, the Blackhole Quietbox, this giant computer, $12,000 worth of hardware, which, according to the information that comes with it, requires a dedicated circuit, a dedicated electrical circuit, 15, 20 amps, whatever it is. And this studio that I'm in now, which is my intention, was to have the Quietbox in here somewhere, because it's where I do a lot of work, as well as this stuff. There is no dedicated circuit here. I'm already using big old extension cords to pull power from other circuits around the house in here to get more power. So I was going to have to do something about it. So I asked around, and I found one of my Albuquerque friends had an electrician that they liked, Patrick, and I got in touch with them, and they came a week or so ago and put in new circuits. So here, this is 2 new 20 amp circuits. The one over here is 120 amp circuit, the one over here is 120 else. Sorry about the incredible disgustingness of the drywall. It needs a paint job bad. And here it is in the panel, back in the back of the house, office quad left, office quad right. So that was a chunk of money, but I was happy to actually manage to do it, to get out in the world and so forth and deal with these people and just get it done. So black hole prepping, check. Faster and smaller. This is the other thing that I was doing today. So this is a picture, a layout of one of these little AI processors. They call them Tensix cores in the language of TensTorrent. So that's why it's got Tensix there. This particular one is for the generation behind Black Hole called Wormhole. And so this is not quite right. These numbers are not quite right for what I am going to be getting, but it's close. It's enough to see the idea. And, there's actually 5. So these boxes up here, those are 5 different little computers, 5 different little processors that all work together. And this is a whole boatload of special purpose hardware that's meant mostly for AI and machine learning that I'm really not even going to be using hardly at all to begin with. I'm just going to be using these little regular things. And so we can kind of zoom in on one of them and here's the key thing. So GPRs, that's the general purpose registers inside the CPU. They're the things that are absolutely the best, fastest, easiest to access. There's 32 of them. Then there's this private little random access memory, which in Wormhole, on these particular ones, it's 2 kilobytes. I believe for Black Hole, it's now kicked up to 4 kilobytes, but it's still really small. And then there's the main random access memory, which is 1.5 almost megabytes of RAM. And that has to be shared amongst all these things and so forth. So there are these levels and levels and levels of different amounts of memory, and all of which, to my way of looking at it, are tiny, are super tiny. So I've been thinking a lot about how to re-engineer the Moolfeast structures and the Ulam shapes of code to try to fit into this. I mean, so once we get done, back up here, so one of these, the machine that should be arriving within the month has 480 of these whole things, 480 copies of this whole thing on 4 different circuit cards inside the machine. Yow. So in Ulam 3 through Ulam 5, and someday, hopefully soon, Ulam 6, the key data structure is called a UlamRef. And I'm going to go way long here. I'm giving myself 20 minutes. I'm sorry, because I just want to go through this. And the UlamRef is a representation of a pointer. Now, like in an object-oriented language, and again, if we don't know what this is, it doesn't really matter, but you have pointers to things. You connect stuff together by pointing at them. And, in C++, for example, one typical thing that's done is you can point at an object, and if you want to have some information associated with that object, you put it like right behind what the thing is pointing at. But in Ulam and the MFM, bits are extremely tight, and we may have an Ulam object that is like 6 bits long, and there's no way we can put more information before it because those other bits are being used for something else. So the UlamRef has all of these data members in it so that it can act like a pointer, so that we can know what type of object it's pointing to, where exactly is it, how many bits is it, and so on. And the problem is, is the UlamRef is huge. It's got 4 things that are pointers. And an UlamRef, one UlamRef is 48 bytes long. So that's 4 times the size of an atom in this new model. These things are huge. And I'm afraid of this amount of hugeness because there's a lot of code to handle and I want to boil it all down. So in the last month, I created UREF, not UlamRef, but UREF, that is meant to be an UlamRef light, to try to get as much of the behavior and the generality of UlamRefs by making the pointer as tiny as possible. And I'm still working on it, and the whole thing may not work out, but I've made a lot of progress, and here it is. The struct UREF, it begins with a 16-bit data item, and that's all it's got. It's a 2-byte pointer. That feels good. It takes advantage of the fact that we don't need general pointers in MFM. There's only a small number of places of things that you really have any reason to be pointing at. So we don't need a 64-bit pointer for that, and so on. So that's it. I also set up instrumentation so that every time I build MFM X10, that's this little branch of the movable feast machine code that I'm using to try to develop stuff for Black Hole, and I have it all cross-compiling so that it's compiling it down to RISC-V code instead of Intel x86-64 code, which is what the machine I've got here is using, and measures how big the code is when it gets done. And so, you know, when I was working, well, there's some data off the end here that I left out because it was way lower, but, you know, already we're at 147 kilobytes of code space used up, like that. And that was at the very beginning, and it just shoots up from there. And again, these programs are doing nothing. They're just warming up and printing out a few values to convince myself like how big the struct is, things like that. They're doing absolutely minimal nothing. And, you know, we've already gone from 147 kilobytes up to 155 kilobytes. Now, we have 1.5 megabytes of that big RAM up at the top, but a lot of different systems within the Tensx processor use chunks of that memory for buffers and all kinds of things. So I'm imagining maybe I could have 1 megabyte of it to use for everything that I need. And so, okay, so if we remap the y-axis here and put a megabyte at the top, then it doesn't look so bad. You know, we've gone from 147 to 155. But again, this is just the tiny beginning. There's no physics here. There's nothing. So we shall see. But I'm glad that it's being tracked. It's writing out to a file so I can see how things go over time. And that's what I was doing for the last month mostly. And, you know, having lots of fun. I did some other stuff too. And the goal for next month is, if I've done the arithmetic right, the black hole should arrive before the next update. And so the goal would be to have it running and be doing little teeny things like these on it. We'll see how it goes. So the goals for today was electrical ready, P4 events, and have more fun. Electrical ready, electrical is ready. Had plenty of fun. Baby P4 events is not working, but the UREF is a big down payment on getting to something like that. So, okay, I'll take it. And that's it. So the goals for September 2, to have baby P4 events. P4 is the new 128-bit atom. Have the Black Hole Quietbox, play with it, have huge fun, and hopefully, I have to put this back on. Release Ulam 6 to tie a bow on the end of that. We'll see how it goes. Okay, 20 minutes today. Thank you so much for checking in, and I hope to see you next time.